Now, what is acceleration due to gravity? This is the value by which every object is accelerated towards Earth, right? If it is falling freely or even if it is in stationary position, the weight of the body which is applicable on every single body on Earth is what? The mass into acceleration, and mass into acceleration, the term acceleration here is acceleration due to gravity. I would like to tell a small thing about gravity again, though I have already told you about this. According to law of gravitation, the formula becomes F is equal to, this is what? The force between any two bodies present in this universe. This is G m1 m2 over r square, which is mass of the body 1, mass of the body 2 upon the distance between them square, right? The word gravity is the same force of attraction between two bodies when one of these bodies is Earth. For example, the force between Sun and Moon would be force of gravitation, but force between Moon and Earth will be the force of gravity. Simple. So now, as we were discussing the value of weight, what is weight? Weight is, we have already knowing this formula since laws of motion. Weight is mass into acceleration due to gravity, which is mg. This formula actually came from what? Force is mass into acceleration, but the acceleration by which the body falls towards Earth is g, that is acceleration due to gravity. We also know the value 9.8, but the existence of acceleration due to gravity came from this chapter. Now, so this is mg. So suppose we have this Earth of mass capital M, and we have a small mass small m placed on the surface of Earth having radius r. What are the forces acting on the bodies now? First of all, the force of gravitation, which is G capital M small m upon distance square. Now, why am I taking the radius to be distance, though these two bodies are in contact? There should be no distance, right? See, the distance is always the average distance between the center of masses of the body, and if Earth is supposed to be spherical, then center of mass would be at the dot center, and that is why the distance between them would be the radius. All right. So this force is actually responsible for the existence of weight, which is, suppose the body is present on the surface, then it would be attracted towards the center with a force called weight. So this force is actually equal to what? Weight, and instead of weight I can write mg. So here I have this thing, mg is equal to g mm upon r square. From here I can cancel out these two terms and I'll get the value of g, which is g m upon r square. So now we have another formula in this unit, which is formula for acceleration due to gravity, g m upon r square. All right. Okay, now what next? Can we find a numerical value of g? We already know it is 9.8, but how did we get to that conclusion? Radius of Earth is usually taken as 6400 kilometers, which is 64 into 10 raised to power how much? For kilometer, I will be multiplying it with 1000. So 3 zeros and 2 zeros makes up 5 zeros. 64 into 10 raised to 5 meters. We also know the value of density of Earth, which is 5.5 into 5.5. This is gram per cubic centimeter. This is the value of density of Earth, the average value. So how can we convert this 5.5 into kg and centimeter cube or kg per meter cube? 5.5 instead of gram I can write 10 raised to power minus 3. So now it becomes kg. And centimeter cube, what is centimeter cube? That is centimeter, cubic centimeter means centimeter cube, right? And I am converting it like this. 1 centimeter is 1 raised upon 100. So cube means this. I have to convert this thing. So this, instead of writing like this 1 over 100, I will be writing it like 10 raised to power minus 2. That is what 100 is written as. And 10 raised to power minus 2 multiplied by 3 becomes 10 raised to power minus 6. Minus 6 will go up and it will become 10 raised to power 6. So overall value is, this becomes 5.5 into 10 raised to power 3 kg per meter cube. Now why I am writing these values? That is because instead of mass I can write, we know this from the density, mass per unit volume. So instead of mass I can write volume into density. So this becomes G is equal to G, volume is V, density is rho over R square. That is what we did, mass is volume into density. Now instead of density, instead of volume, what we can write is 4 by 3 pi r cube, because this is supposed to be spherical. So this becomes 4 upon 3 pi and multiplied by r cube. So this r cube and r square cancels out. You are left with only single term r. So acceleration due to gravity have another formula which is 4 upon 3 pi g r rho, right? So sometimes when you can't use this formula, you can go for this formula. And putting the value of g, r and rho in this formula, we'll get 4 upon 3 into pi is 22 over 7, g is 6.67 into 10 raised to power minus 11, r is this 64 into 10 raised to power 5, and this thing 5.5 into 10 raised to power 3. This will give you the acceleration due to gravity in meter per second square, and it comes out to be approximately 9.821, something like that, meter per second square. So generally it is taken as 9.8 meter per second square, and we further approximate it, round it off to 10 to ease up our calculations in old chapters like kinematics and laws of motion, right? So this is the numerical value of g. Now another important thing for this acceleration due to gravity is how does its value changes. Are there any factors involved with this? See, first of all, a very simple factor is I place the body exactly on the surface, so that I had to take the distance between two bodies as r. What if I place this body instead of here, somewhere here, right? If the body is placed here at some height h, so there will be definitely a new formula. So one thing is for sure, that acceleration due to gravity changes with height. So it will also change with depth, and hence it will also change with rotation of earth. So let's do all those things, and we'll start with acceleration due to changes in acceleration due to gravity. So you can note down this topic, variations in g, and we'll start with the height first. Okay. Now one thing is one physical factor which you guys have already noticed is when we go to some height, what happens to our breathing problem. Sometimes we feel easy, sometimes we feel hard when going to a height, or sometimes we feel a sudden stopping or sudden some stopping of noise in our ears, right? This happens due to value of acceleration due to gravity. It decreases with height. And how it decreases, let's find out. First of all, what we are doing in right now is variations in acceleration due to gravity, and we'll first start with height. So for this thing, we are considering that the object which was initially at distance r is now kept at height h. Alright, this height is h and the body is placed here. So we already know the formula for acceleration due to gravity, which is g is what? Gm over r square. So at this height, that is at this height, the value of g dash might be some new value. It would be gm over r plus h. That is what I have done. I have just increased the value of distance, r plus h whole square. If I divide these two, g dash over g, I will be left with what? Gm over r plus h whole square, whole divided by gm over r square, right? I will get this term on the numerator side. So g dash over g is r square over r plus h whole square. This is one of the formula. G dash is g times r over r plus h whole square, because on both numerator and denominator I am having square, so I can take it as common. So this is applicable to both. So this is one of the formula to find acceleration due to gravity at some certain height h. But this formula can be further simplified. Just note down this formula. Now what I am simplifying is, in this equation from denominator side I am taking this thing common, r. So r square will come out, and I will be having 1 plus h over r. Now if some of you guys are having trouble in sorting it out, how did this happen, I'll simplify it, but I'll write it here only. See, in this equation I had r plus h whole square, right? So I am taking just r single out, I'll be left with 1 plus h upon r, right, whole square. Now just multiply this r again with the term. What will I get? R, and when I multiply this, r will cancel out, I'll be left with h. So I am getting r plus h whole square, which is exactly what I have written. So from now down these two things, I'm taking this r outside the bracket, so it will obviously be coming out square because that was r square into this term square. So now I'm left with this, right? Instead of that whole thing, r square 1 plus h over r, this raised to power 2. Now cancel this out. What will you left with? You will be left with 1 upon 1 plus h over r raised to power 2. This whole term, when it goes up, it will become minus 2, right? So instead of this, I am writing 1 plus h upon r raised to power minus 2. This is what? Value of g dash over g. How can we sort it out? Using binomial theorem. The reason I took 1 in the first term is the thing that in binomial theorem we have a simplification thing that if the first term of a complex power is 1, then we can place the power in the front of second term. So what we have done is 1, the power goes in front of second term, minus 2h upon r. This is the simplified form using you have to write it up using binomial theorem. Okay, this is the simplicated form of binomial theorem. So this is g dash over g. So g dash becomes equal to what? G times 1 minus 2h upon r. So I am erasing all this and I am getting now the final formula is g dash is equal to g times 1 minus 2h upon r. So this is the final answer for oscillation due to gravity. And tell me, using this formula, the oscillation due to gravity has decreased or increased? See, this is how you have to find out. If you increase this value, if h tends towards r, so this value will become greater than 1 and this value become negative. So this is how you can figure out that oscillation due to gravity is decreasing with the increasing value of height. Same ways here also, we had this important formula for oscillation due to gravity, which is g dash is equal to g times r square over r plus h square, right? So we have two formulas for oscillation due to gravity, variation with height. Which of the following formula will you use if I tell you that the height is 100 kilometers? See, if h and r are comparable, what is h and what is r? R is radius of earth, which is 6400 kilometers. If height is 100 kilometers, so if h and r are anyhow comparable, so that is 100 is still comparable to 6400 because 100 upon 6400 will give you 1 upon 64, though very less quantity, but yes, you can take it. But less than any value less than 100 kilometers, for example, if I have to take height is equal to 10 kilometers, 10 is not comparable to 6400 at all. So for that you will be using this formula. So this formula is used when height is small, when it is not comparable to the radius of earth, and this formula is used when r is, that is when h is large, with that is when height is comparable to the radius of earth, that is 6400 kilometers. So if generally I have deduced this is used for values less than 100 kilometers and this formula is used for values greater than 100 kilometers. That is a simplified version. Alright. So what we just did, we found out the value of oscillation due to gravity, that was g m upon r square, and we also found its value, which is 9.8. And lastly, we did its variation with respect to height, that how oscillation due to gravity changes with respect to height.